So method of partial fractions. From the title of the topic itself, you know that you will be dealing with integrals and fractions. As such, we call it the method of partial fractions. Now, how do we go about using the method of partial fractions in evaluating a particular integrand that is in the form of a fraction itself? So the primary name of the process of evaluating an integral using the method of partial fractions is what we call partial fraction decomposition. You decompose. So we know as CHEs, we know what decompose is. So from one big thing, you're going to decompose it, or you're going to slice it down into smaller fractions of that particular big thing. So in here with partial fraction decomposition, the original fraction that is being given is decomposed to its equivalent partial fractions by first and foremost, making sure that the denominator is in factored form. So let's go through the steps of doing the partial fraction decomposition as it is named. So number one, you set up the partial fraction decomposition with the unknown constants A, B, C, etc. So these constants A, B, C, D until whatever letter is appropriate for you to use is the numerator of your equivalent partial fractions. So you have one fraction which you are to decompose into partial fractions, and the numerator of this particular partial fractions are having unknown constants, or we call them undetermined coefficients. We determine the value of these undetermined coefficients and then evaluate each of your partial fractions equivalents separately. So second, multiply both sides of your resulting equation by the least common denominator. The least common denominator that is being mentioned here, class, is the original denominator of your given fraction in your integrand. So you're going to multiply both sides by this particular original denominator. That way, you will know what you need to have written on the numerator of your particular partial fraction. Then simplify the right-hand side of the equation. You simplify the right-hand side of the equation, which constitute your partial fractions. Then write both sides in descending powers, equate coefficients of like powers of x, and equate constant terms. We will do all of this. Then solve the resulting linear system for the undetermined unknowns or undetermined constants A, B, C, etc. After doing this, you can substitute the value of A, B, and C, and then write the equivalent partial fraction decomposition, and then evaluate your separate integrals. Now, it would be difficult for you to absorb all these 6 steps unless we do it step by step. So let's go first to the study tip before we go to specific example. Now, you will encounter some examples in which the denominator of the given rational expression, the rational expression is the fraction, is not already factored. So, if necessary, begin by factoring the denominator. Or first and foremost, as a study tip, first and foremost, you have to check the degree of the numerator and the denominator in your given fraction. If the degree of the numerator is equal to or higher than the degree of the denominator, then you have to first do long division. After you have done long division, you make sure that in the remainder, if there's a remainder, you have to make sure that the denominator of such a remainder is written in factored form. Once you have done that, you are ready to apply the 6 steps that I have just read a while ago. Okay? So now we go to this particular example, which you need to integrate. So what I'm going to do first is have this written in the Jamboard. So I'm going to use the Jamboard class. That way we'll have a lot of space to use. So please take a picture of the given. That way we will not go back to this original given fraction later when we are in the Jamboard. Okay? So 1, 2, 3. Okay, you have taken already the picture and then we go to our Jamboard. Okay, just give me a few minutes because I haven't yet opened Jamboard. Okay, share screen. Okay, so this is our Jamboard now. I hope everybody sees it. And we're going to write our given integrand. The integrand that we are to evaluate. So you are given 2x cubed minus 4x squared minus x minus 3. You're going to divide that by x squared minus 2x minus 3. And you have here dx. Okay? That's your original integrand. Now, what did I say in the study tip? You have to make sure first that you have checked the degree of the numerator and the denominator. In this case, our numerator is of degree 3. Our denominator is of degree 2 only. So as such, there's a need for you to do long division. So you have 2x cubed minus 4x squared minus x minus 3. And you're going to divide it by s squared minus 2x minus 3. Now, what will make your x squared 2x cubed? So your answer would be you need to multiply it by 2x. So after multiplying it with 2x, you can now have it rather multiply now the 2x to this original divisor that you have. So you have 2x cubed, okay, minus, so you have 4x squared, and you have here minus 6x. Then you subtract. When you do subtraction, you can see that this will cancel each other. This will also cancel each other. So what remains is the negative x, this negative x, and this negative 6x becomes positive. So your answer is 5x if you subtract this 2 minus 3. Now, this 5x minus 3 is of degree 1 only. Your denominator in the original fraction is of degree 2. So meaning, this will be now the remainder of your long division process. So I can write this integral now as equivalent to this. Your answer here, which is 2x dx, and the remainder that you have. So plus the integral of 5x minus 3 divided by x squared minus 2x minus 3 dx. Okay, can you follow? Any questions so far? Okay, so there's none. The first term here does not have any problem because it has already an answer. So the answer here when you do integration is x squared. Because you use power rule here, that would be x squared over 2. The 2 in the denominator cancels with the 2 that you have there. Now, what about the second one? So the second expression will need the method of partial fraction this time. So the second step after you have already checked the degree of the numerator and the denominator is you factor the denominator. Factor the denominator whenever possible. Okay? So just give me a minute, class. Okay, now, how do you factor the denominator? So when you factor the denominator, I'll use a different color here. This x squared minus 2x minus 3 can be written in the form x plus 3 x minus 1. But if you look closely, the positive part is bigger than the negative part. And the middle term here is negative. So then you have to change. I made sure that you will have to change. I made sure that it's not the correct thing yet so that you will know how to factor. So in this case, it should be x minus 3 and x plus 1. So that denominator of yours was already factored in this form. Okay? This is your first step, the long division. This is the second step. You make sure that the denominator is in factored form. So now we will use the method of partial fractions to this expression here. Okay? Now, I will just rewrite that particular thing in here below so you will know that this is the one that we're going to process. So now you will have this one as, so 5x minus 3 divided by x minus 3 and x plus 1 dx. This one is just equivalent to this. Our answer for this later will be added to the answer of the first integral that we have already evaluated. Okay, so this is the integral wherein we're going to use the method of partial fractions. Now, I'll go to the next slide and show to you how method of partial fractions should be done in here. Okay, so you have, I'll just write here the fraction 5x minus 3. And I have here x minus 3 and x plus 1. Okay? So that's the fraction that you have here in the remainder of our original integral. Now, how does the method of partial fraction works? It says there in the steps that you have to write or you have to decompose this particular original fraction into its partial fractions. The process of decomposing requires that for each of the factors that you have in the denominator, there should be an unknown constant or undetermined coefficient in the numerator which you need to determine. So I can write here a over x minus 3 plus b over x plus 1. Okay? They could be interchanged, by the way. You can have the x plus 1 here and you can have the x minus 3 here. It doesn't matter. So the original fraction was decomposed into these partial fractions. Now, you see that I did not for now consider what's written in the numerator on the right side of the decomposed partial fractions. It's only the factor or the factors of our denominator, which is this one. Now, after that, you're going to copy. So you copy the numerator, 5x minus 3, on the left side. And it says there in the instruction, write this in a different font. You will multiply this decomposition that you have by the original denominator. Okay, the purpose is, so if the process of multiplying it by the original denominator, you have this left here because of course you will have the numerator left on this side. The purpose of this is that you'll be able to multiply these unknown constants or this undetermined coefficient by the factor that is not present in its denominator. So since you have x minus 3 here in the denominator and your multiplier is x minus 3 and x plus 1, then it will require that you will have x plus 1 now multiplied to a. So that factor that is not present in the denominator will be the one that is multiplied to the unknown constant or the undetermined coefficient. Okay? Then we do the same for the second partial fraction. So if you multiply x plus 1 by this expression, then it needs that you multiply it by x minus 3, the factor that is not written here in the denominator, and then you multiply it by b. Okay? You have placed the undetermined coefficients or the unknown constants in the numerator of your decomposed partial fraction. And then what you do, you multiply the entire equation by the given denominator. That way, for each of the partial fractions, you need to multiply its unknown constant by that factor in the original denominator that is not present on its denominator. Okay? The next step is now the portion wherein you will need to determine the very important value of these unknown constants A and B. Now, how do you do that? So very simple. You are to equate coefficients of your variables and your constants here. In some books and in some references in calculus, you assign a value for the x if your factors are linear. I say linear because the exponents of the x here, your variable, is just 1. So if the factors are linear, the factors that are multiplied to your unknown constants, you assign a value for x that will eliminate a particular constant. What do I mean? So in this case, if I will assign a value of -1 for the x, this entire expression will be 0 because you have -1 plus 1, that would be 0. So I can right away determine the value of B in that case. But since in our steps, he says there that you will equate coefficients of the variables, then we will do that. The assigning of a value to a particular variable to 0 a particular term will only work if your partial fractions are all linear. That is, if their exponents, the exponent of the x is just 1. If the exponent of the x is squared or cubed, that won't work anymore. And you will have a hard time solving for the values of the unknown constant. So in this case, I would like to start, I will just discuss how you will find the value of A and B by equating coefficients. So what do I mean by that? So for this part, I will equate coefficient of x. So meaning all the variables that has the x, I will equate the coefficient. Now on the left side, I have this term which has the x and its coefficient is 5. So I'll place here 5. Okay? Now 3 does not have an x, so it will not be included anymore. Now in this side, if you just mentally do the FOIL method, or if you want to add another line here, you can do that for expansion, you will notice that this A will be multiplied to x. So meaning the coefficient of x here will be A. Okay, I'm not anymore interested with this one, with the A, because it does not have the x anymore. Now, I'll do the same for the second term, for the B. So your x multiplied to B will have the x variable coefficient as B. Then this one is -3B, which is not important to me. Okay, because I only want the coefficients of the term that has the x. So, ang mula ning may x, ini may x ni, kag ini may x. Ang wala x, hindi ko na ipag-i-equate. Kaya in the first place, gusto ko ya ang may x. Now, I wasn't able to solve for A and B for now because this is a single equation with two unknowns. So, I will have that as equation 1. Now, I'll go to the constants. Or we place that as x raised to 0. Because x raised to 0 means its value is 1. So I'll go for the constants. Here, on the left side, I have -3. So I will place -3. Now, I will equate it to, here on the right side, a multiplied to 1 will be a constant, which is a. And in here, I have -3b, so that is also a constant, which is 3b. So this is my equation 2. Now, I have two equations with two unknowns, meaning I can solve the unknowns A and B. So, I will copy this one here, I'll place it here, 5 equal to A plus B. Now, if I intend, if I intend to eliminate the A, what will I do with equation 1 and 2? If I will eliminate A, what do I do? I will, what is the,
Subtract, miss.
okay, subtract, very good. So I will subtract. So if I will subtract, I have negative 8. And of course, you could see that this will be gone out of the picture because A minus A is 0. Negative 3B, this would become negative because I'm doing subtraction. So that would be now negative 4B. If divide by negative 4, so I know that B is equal to 2. Now, since I know B is equal to 2, I can substitute to any of these two equations, whichever is simpler. That way, I can find the A. So, from here, 5, from here, 5 minus, so B should be transferred there, minus 2 is equal to A. So, A is equal to 3. So, you have now the very important unknown constants for undetermined coefficients A and B. What are we going to do with these two? So let me proceed to the next slide. You will now substitute A3 in here and B2 in here and evaluate these integrals separately or individually. Okay, so now I will proceed on the next slide. So remember that in here you have already x squared as the answer. So therefore, if I will copy the original integral, it would be something like this. Let me just check on the picture that I have taken so we'll not go back to it. So I'll have this one. So therefore, the integral, the original integral, which is 2x cubed minus 4x squared minus x minus 3 divided by x squared minus 2x minus 3 dx is equal to, in our first integration, we already have this answer, which is 2x. Rather, x squared. So I'll place it here. And now I will add to it the individual partial fractions equivalent to this remainder of our integration. So A is 3 and its denominator is x minus 3. So I'll place it here, 3 integral of dx over x minus 3. Now, what about the other one? This one, the b. B is 2. The denominator is x plus 1. So you have 2 integral of dx over x plus 1. So the remainder now was decomposed to these two partial fraction equivalents. So I will answer it as x squared plus, we know that this is an ln because we have du over u. Your u is x minus 3, the du of that is dx. So your answer here is 3 ln of x minus 3. This one is the same. This will yield an ln because if this is your u, the x plus 1, the du is dx. So you'll have 2 ln of x plus 1 plus c. Actually, this is the answer already. But if you want it simplified, it can be simplified using our properties of logarithm. So we'll have plus, this 3 goes here as the exponent of the x minus 3. So it could be written like this. And this 2 could be the exponent of this x plus 1. So you'll have ln of x plus 1 squared plus c. Now, if you wish to combine these two, since they are being added, it could also be simplified further in this form. Ln of x minus 3 cubed x plus 1 squared plus c. So we know that if we have several functions or terms in the argument or as the argument of the ln that is multiplied, it's equivalent to that ln which is being added, having those arguments. So this is the answer to this particular fraction that you need to integrate using the method of partial fractions. So in here, your factors, the factors of your given fraction in your integrand have what we call linear factors. We call it linear because the exponent of the variables are all 1. Should there be a variable in which the exponent is not equal to 1, then if it's 2, we call it a quadratic factor. Okay? Now, any question or any part that you wish us to go back to? So, is it clear what is being done? So, do long division. If there's a need for you to do long division, factor the denominator. Then write its equivalent partial fractions. Determine the value of the unknown constants or undetermined coefficients by using the process of equating coefficients of variables and constants. Then evaluate the individual integrals. Then that should be your process of method of partial fractions. Any question? Okay. If there's none, then we'll go back to our slide. Where is our slide? Okay. Okay. So that's our slide. So if you have taken a picture of our answer there, so this is the process of long division. This is our remainder. This is our answer. So we did that already. Then we factored. So that's the factored form. Then this is your corresponding expression that needs to be integrated. So we integrated this first, yielding an x squared. If integrated, this will yield ln's. Okay? So that's your linear factors. So ini siya ang circle, ini linear factors ni siya. When the denominator of a rational expression or a fraction contains a power of a linear factor, set up the partial fraction decomposition with constant numerators. When the denominator of a rational expression contains a power of a prime quadratic factor, set up the partial fraction decomposition in this form. Now, this one now talks about a prime quadratic factor. So meaning it's an unrepeated quadratic factor. So if you have a quadratic factor, the exponent of your x, your variable, is 2. And as such, you don't just simply write a on the numerator, but you write ax plus b. If you have another quadratic factor, then your numerator would be cx plus d. We only assign unknown constants, so constants without any variable, if our factors are linear. That is, your variable has an exponent equal to 1. Okay, so if it's quadratic prime factor, this should be your numerator. Now, we'll continue. So you have that. So we have separated it into partial fractions. So non-repeating linear factors. So the term non-repeating class, it says here non-repeating linear factors mean that your linear factors are not the same. They are unique from each other. So if that is the case, we call it non-repeating linear factors, because if our linear factor is being repeated, they look similar, one is just raised to another exponent, you will have a different process of solving your particular given integral. Okay? So what do? We multiply by the common denominator. And this is the result. We equate coefficients of 5x to ax plus bx. So you have that. And then we have 5 is equal to a plus b. Now this one class, this part is for the constants. You have -3. You have a minus 3b. So these are your two equations. This is for the x and this is for the constant. To solve two equations with two unknowns, you have this. 5 equal to a plus b and -3a is equal to a minus 3b. So that's what we've done. So your answer for b is 2. And if you substitute the b, which is 2 in this equation, you'll solve for a, which is 3. Then, of course, you are ready to answer the integral in terms of this one. Okay? If you integrate this with a equal to 3 and b equal to 2, this is the answer for your given remainder for the original given integral. Your final answer, of course, I'll discuss that one later, huh? The heaviside thing. So the same answer, okay? Now, what is this heaviside thing? That's how it's being referred to in some reference books in integral. This is what I mentioned a while ago. Then when you have linear factors, unique linear factors, what you do, you assign a variable for the x that will zero a particular term. So let me annotate. So if you will assign here, so this is already your original expression. Okay, this is your resulting expression after you have multiplied this entire equation by x minus 3 and x plus 1. So this is your original expression. The heaviside method makes you substitute a value for your variable here with the goal of making a particular term 0. So if you assign x equal to -1, this becomes 0. Just like what you see here. -1 minus 3 is -4. So -4 times b. If this is -1, this is -5 minus 3, that would be -8. So -8 minus 4, okay, -8 is equal to -4b. So b is equal to 2. The same as what we have done in the previous method. Now, you can also assign x equal to 3 here to make this 0. So, na-0 na di siya. If this is 0, this one will not be 0 because you'll have here 3 plus 1, that would be 4. And you'll have a. If this is 3 times 5, so that would be 15 minus 3, that will make it 12. So 12 then is equated to 4a, which gives you a equal to 3. So this is the heaviside method. With the goal of making a particular term 0, you assign a value for your variable. Again, the downside is it requires that your partial fractions are all linear. So meaning, wala sang naka-x squared, wala sang naka-x cubed, only x. Okay, so the same integral processed differently. The process of equating coefficients is more, shall I say, friendly because it doesn't have any limitation. You can use it even if you have linear factors or repeated linear factors or quadratic factors. Okay? Any question? Sige. So I will now mark my clear my markings here. So if we proceed, we still have the answer, same answer as what we have, as what we got in the previous method. So what about if we have a case of repeated linear factors? Okay, now we will discuss these repeated linear factors after a 10-minute break. So we go to type 2 under the method of partial fractions. So you have, in this case, the repeated linear factors. So when a rational expression contains a power of a factor in the denominator, be sure to set up the partial fraction decomposition to allow for every natural number power of that factor less than or equal to the power. So if you notice, class, here in your denominator, you have a linear factor x minus 5, but its exponent is 2. So it's correct in saying, or would like to say, that your linear factor x minus 5 is being repeated once. So you write it in the method of decomposition of this original fraction as x minus 5 with the unknown constant a here. Then you will have here in the next partial fraction x minus 5 raised to 2. And you will have your unknown constant b in here. For the next linear factor, which is repeated because it's now x cubed, so meaning it's repeated twice, you will have x squared, and x cubed. So depending on the exponent that you have here for your linear factor, that's the number of times that you're going to write your particular factor repeated until such time you reach the exponent that is indicated in the given. Okay, so if it's x cubed, then you have to write it 3 times. First with x, then second with x squared, and then third with x cubed. Okay, so we say that x minus 5 is your repeated linear factor, and x is also your repeated linear factor. So this order of writing your partial fractions is immaterial because you can have the x first written, x squared, x cubed, and then followed by x minus 5 and quantity x minus 5 squared. Now, let's see in this particular partial fraction that we have. So I will not anymore use the Jamboard because you know fully well on how we're going to decompose this. So what will happen is this. You have the case of a repeated root in x plus 2, which is raised to 2. So what will be done in here? You're going to write your corresponding partial fractions in this manner. So I'm going to write it like this. Okay, I'll just write this on top. Wait, class. Okay, there you go. So we'll write this one as a over x plus 2. And you'll have another partial fraction here, b over x plus 2 squared. Okay. The reason why you have this is because if you remember our procedure in the first example that I discussed, wait, class, to change the color, change to blue. You will need to multiply this by the original denominator. Okay, so this will be now the resulting expression. So you will have 6x plus 7 on the left. Since you only have x plus 2 here in its denominator, then your unknown constant in the numerator need to be multiplied by another quantity x plus 2. In the case of the second partial fraction, you only need to multiply it by 1 because this x plus 2 squared is exactly the same as our original denominator. Okay? So I will clear that one now, and then we proceed to the next step. So if you do expansion, you will have here, so if you use the FOIL here, you'll have that. You'll have ax plus 2a plus b. In here, in this case, you have equated the coefficients of x. So you'll have, or you have equated the variables or the terms that has the x. In here, you get to see that a is equal to 6. Why? Because you simply get to cancel the x. So if you just simply pick out the term that has the x, actually you will be able to equate 6 and a. Now, this one is for the constants or the x raised to 0. So if you'll have the constant here on the left is 7. The constant here on the right is 2a plus b. Since you know already the a here, so you just need to substitute. So that would be 7 and 12 plus b. So your b is -5. So you now know that a and b here is 6 and -5 respectively. So what will happen? You will integrate these two expressions. Okay, unlike the process of integration here. Change the font. Let's say, so if you do the integration of that, your a is 6, so you have 6 integral of dx over x plus 2. And for the b, which is 5, we have -5 integral of dx over the quantity x plus 2 squared. If you are going to integrate this will give you, so you'll have an x plus 2. So this will give you, by the way, there's an error here because this one is x plus 2. So 6 should be multiplied to the ln of x plus 2. So this is an ln. Well, this one, if integrated, will give, so what's the integral for this one? You will use power rule. Your power here is -2, right? The du is just dx, so you'll have this one. So it's -1 over -1. So you will have a plus 5. Then this is actually -1. Okay, so you will have x plus 2. So it's in the denominator plus c. So your answer for this particular integral is 6 ln of x plus 2 for the first term, and you have -5 divided by x plus 2, or rather +5, because this one will be x plus 2 raised to -1 over -1. So that becomes positive. So it becomes 5 divided by x plus 2, and then you have the integration constant, which is c. Okay? So this one is not yet the answer to your integration. This is still to be integrated. Now, any question? So this is your answer. If I will clear my markings, this is your answer. Or if I will not click it, probably the integration process is shown here. Okay, sorry. Okay. Okay, we'll just we'll just click everything so you get to see. Okay. If I'll clear my markings here, the annotate. So this needs still to be integrated. That's not yet the answer to your integration process. Okay? avoid this common error. So you have this study tip, you have A over X plus B over X minus 3 for this one. And notice that your C was not raised to 2. So the correct way of writing it is it should be raised to 2. So these are some of the mistakes that the students are making. Okay? Anyway, most of the time, class, if it's just a linear factor, if you're given a linear factor, your answer is mostly ln, or you're just simply using power rule. Okay, I will close this one. So let's see. Okay. Any question so far with the repeated linear factor? None? So we go to the quadratic factor. So this time, your linear factor is not anymore repeated, but you're given a quadratic factor, a prime quadratic factor. So what's a prime number? A number that doesn't have any factor. So that's prime quadratic factor. Okay. What have you noticed in this particular example? So it's a challenging example because what have you noticed? Anybody? What have you noticed? You already have a combination here. Look at your denominator. So if I will annotate, this one is repeated linear, right? This is repeated linear. Well, this one is quadratic. So a combination of the different factors in your denominator. So if you have a combination of the different factors, just simply represent each of the factors correctly as they should be represented if they were just alone, if they are not combined with another. So what do I mean by that? So this is what you're going to do. So this one is the irreducible quadratic factor, meaning hindi na siya ma-factor, hindi mo na siya ma-reduce. And this one is the repeated root that I have mentioned. So when you write its equivalent partial fraction, look at the manner in which you write the irreducible quadratic factor. You write it as x squared plus 1. And your numerator, take a closer look, your numerator is not just an unknown constant, but you have an unknown constant with x plus another unknown constant. So for an irreducible quadratic factor, you have a two-term numerator. Duha ka-terms ang ara sa numerator. Your constant and the constant multiplied to your variable. Now, for this repeated linear factor, you simply represent it the way you will represent a repeated root. And that is first, you will have the x minus 1, and then next, you will have the quantity x minus 1 raised to 2. So since you already used the A and the B here, of course, your next unknown constant will be the C and the D. You can have these two written first, followed by this one, doesn't matter, as long as when you evaluate later, your individual partial fractions, expect that you should have 4 partial fractions. This is considered as one partial fraction, and then this B is considered as another partial fraction. Okay, so a combination of repeated linear and quadratic factor. Now, what happens next is, so this is a first degree numerator. So if you're going to multiply, this entire expression by the denominator x squared plus 1 and x minus 1 quantity squared, this will be the resulting expression. The left side will be negative 2x plus 4. The right side would be this this first degree numerator, the ax plus b, will be multiplied by the factor that is present here in the denominator of this fraction. Since you already have x squared plus 1, you still don't have the x minus 1 quantity squared. So it's multiplied by that. For the c, you only have x minus 1. In your original factor denominator, you have x minus 1 squared. So you still lack another x minus 1, and you lack the x squared plus 1. So that is why you have these two as the multiplier for the c, the irreducible quadratic factor, and 1 for the x minus 1, because it should be squared. But what you have here in c is just raised to 1. For the d, you have the entire quantity x minus 1 squared repeated root. So what you only lack is the x squared plus 1. Here, your irreducible quadratic factor. So this is now your entire equation. So this is what I meant with equating coefficients, because this time you cannot anymore zero a particular term by just simply assigning a value for the x. Why? Because you still have other terms which will not be zeroed. Okay, so in this case, you have x minus 1 here, which is a linear factor. If you assign an x plus 1 here, it's okay because this will be 0 and this one will be also 0. This entire thing will be 0. You will be left here with a d, which is 1 plus 1, which is, of course, a 2d. Okay, and you can find d right away. You can use Heaviside in this case because you have a linear factor. But if you don't have a linear factor, then you cannot really use the Heaviside process. Now, if you'll have this cleared, what happens next is the equating of the coefficients. So in here, you have expansion. So what was written here was expanded for ease in using equating of coefficients. So here, this is another expansion. So FOIL method for this one, and this one is, of course, FOIL method also. And, of course, the rest would be just finding the value of the A, B, and C together with the D to evaluate this particular integral. So let's see if we're going to process this particular integral in the Jamboard, because I have not written here the entire process of evaluating it. Okay, I'm just taking a picture, that way when we go to the Jamboard, we will know the partial fraction that we're going to work on. Okay, let's see. So I will go to the Jamboard. Okay, we'll proceed here. So there, what we have is the negative 2x plus 4 divided by x squared plus 1, and you have x minus 1 squared. And you have ax plus b over this irreducible quadratic factor, and you have c for x minus 1, and you have d for x minus 1 quantity squared. Okay, when you multiply this entire equation by x squared plus 1 and x minus 1 squared, your left side would be 2x plus 4. And this one would be ax plus b multiplied to x minus 1 squared. This one would be c times another x minus 1 times x squared plus 1. And your d, which is x squared plus 1. Before I proceed in determining the unknown constants, do you have any questions as to what was done in here? Okay, we can simplify the process of solving the constants A, B, C, and D here by assigning a value for x which was 0 a particular term. Because in this case, we have linear factors which are repeated. So it's okay. But if we don't have any linear factor, I suggest that you do equating coefficients. So we will assign first a value which is equal to 1. So by the way, this method is the heaviside method. So you substitute x here equal to 1. So that would be -2 plus 4. So that's +2. Okay? Now, when you substitute 1 here, this will be 0 because this is 0. This will be 0 because that would be 0. So what is left is this 1. So you have 1 squared plus 1. So that would be 2. So you have 2d. So d is equal to 1. Okay? Now, if you assign x equal to 0, so you will assign x equal to 0 to everything here. So you will have 4. You have 4 here. And in here, you will have 0. You will have here b. This will be 0 minus 1. -1 squared is 1 times the b. So you have the b. Now, if this is 0 and this is 0, you have -1 times 1. So that's -c. If this is 0, that would be d. Okay, because 0 plus 1 is 1. So that would be d. You know already d is equal to 1. So this one here will become 4 equal to b minus c plus 1. So we'll have 3 is equal to b minus c. Okay? We can solve for now anything because we have two unknowns. So we can substitute. You can substitute another value for x, or we can even combine the process of equating coefficients here. So pwede ka substitute values ng x at the same time ma-equate ka coefficient, whichever will make things easier for you. Okay, oftentimes class, when you assign a value of 0 for the variable, what you are actually doing is equating constants. So you are equating constants in your particular equation. So if you notice, this is the constant here. In here, your constant is positive b because that's +1 when expanded. It's multiplied to b. In here, constant is -1, so that's -c. In here, your constant is 1, so that is d. Okay, so we need one more. Actually, we still need 2 more equations because we have 4 unknowns. So we can equate coefficients in this case to help us find the value of the 4 coefficients. So let's say, I'll go to the next slide. I will equate coefficients of x cubed. So I will not have it expanded because it will entail time. I will just simply do it mentally. Okay? Do I have an x cube here? I don't have a term that has an x cube on the left side, so I will place it as 0. Okay, now I'll go here next. Now in here, what will be the term that will have an x cube? If I'll have this expanded, this will give an x squared. This x squared, when multiplied to ax, will give an ax cube. So meaning, in this product here, I will have a as the coefficient of x cubed. Now, I suggest that if you cannot follow through by simply mentally doing this, then you expand it the way it was presented in the slides. Naging expand gini siya. Now, in here, you have x squared. You have another x here. So, meaning, you will have a c for a term that will have an x cubed there. So, I'll place here c. Let me check if it's a plus c or a minus c. So, it's a plus c. So, plus c. Okay? Now, next. Do we have an x cube here? The answer is no. We don't have an x cube here because it's only x squared. So, I have another equation, this time in terms of a and c. So far, I know only d. I don't know a, b, and c. So, I can solve anything. So, I will just simply write here, a is equal to -c. That's my equation 2. Now, since I'm done with x cubed, I'll go to x squared. Okay. Now, in the left side of our equation here, we don't have an x squared. So, we'll have it here placed to 0. So, that would be 0. Now, here on the right side, you check if you'll have an x squared here. Now, if this is expanded, we'll have this expanded. This is x squared minus 2x plus 1. This x squared here, if multiplied to b, will have a coefficient which is b, right? So I'll place b here on the other side. Okay. Oh, I need to delete it. So I will have here on the other side, here you have a middle term which is negative 2x. And you'll have a first term here which is x squared. So plus times b, so you will have a b here. You'll have a b, but you'll have another x squared class because your middle term here, which is negative 2x, if multiplied to ax, will give you negative 2ax squared. So you have a coefficient which is negative 2a. Do you get it? You have here negative 2x multiplied to ax, so that should give you negative 2ax squared. This x squared here multiplied to b will give you bx squared. So the coefficients of the two I have written here. So far, that is only for this one. In here, your x squared will be present if you multiply this x squared with negative 1 times the c, so you will have a coefficient of negative c for the x squared. Okay, for this particular thing that we are multiplying. For this one, we have the d. So I'll place here d. Okay, as I've said, if you cannot follow through without expansion, then expand first. Then we will simplify with d being equal to 1. So we'll have here 0 is equal to b minus 2a minus c plus 1. So let's see, you have 1 here. Discuss, ha. So you have 1 there. And if you substitute, if you transfer 1 on the other side, you have negative 1. And you have b minus 2a. But take note, class, that your a here is negative c. So I can change this a here to negative c. So I will erase this a. I will erase this a and make it negative c. So I'll place here negative c. I have negative c. Now what happens is you'll have negative 1 is equal to b. Negative 2 times negative c is plus 2c, and I have here another c. So negative b is equal to b. 2c minus c is c. Okay? Now, what will I do with this negative 1b plus c? I have it here. Okay, so I will use it together with this equation 1, which is 3 is equal to b minus c. So I'll place here 3 is equal to b minus c. So it depends on what method you will use. You will still eliminate either of the two variables b and c. So if we subtract, we eliminate the b. So you'll have negative 4 is equal to 2c. So c is equal to negative 2. If you note c as negative 2, it follows that a is equal to 2. If you know c as negative 2, you can substitute it to any of these two equations. So from here, if c is negative 2, that will be transferred on the other side. So you will have b is equal to 1. Okay, negative 2 in here. Putang mo di siya ma-positive 2 siya. Minus 1, it's 1. So b is equal to 1. So now you have completed all the undetermined coefficients or the unknown constants. And you are ready now to integrate. So how do we integrate? So we integrate each of these partial fractions. Okay, now we'll do the integration process. So therefore, the integral of, okay, the A is 2, and I need the B. The B is 1. So this is how it should be written. 2x plus 1. This is your A, and this is your B. It's divided by x squared plus 1. dx. That's your first integral. I have substituted A and B. As for the C, your C is negative 2, and its denominator is x minus 1. So you will have minus 2 integral of dx over x minus 1. But you still have a third integral. The third integral is your d, which is 1. And it has a denominator of x minus 1 quantity squared. So you will have here dx over x minus 1 quantity squared. So now you are ready to integrate. Now, the first integral here cannot be integrated as is where is. You need to split. You need to distribute the x squared plus 1 to the two terms in here in your numerator. So what do I mean? You have to write it like this. 2x dx over x squared plus 1. Then you'll have another integral dx over x squared plus 1. And you'll have another here. You copy 2 integral of dx over x minus 1. And the last will be dx over x minus 1 quantity squared. This one, if this is your u, your du is 2x, right? U is x squared plus 1. Your du is 2x dx. So this is an ln of x squared plus 1. This one is one of the inverse trigonometric functions that we have discussed. The du over 1 plus u squared, which is actually yielding an arctan. So your a here is just 1, so it's 1 over a arctan of u over a. So in this case, you have simply the arctangent of x. Your u is x, your a is 1. So 1 over 1 arctan of u over 1. So this is it, the arctan of x. And for this one, this is an ln. So 2 ln of x minus 1. This one will be power rule. The derivative of x minus 1 is dx. So meaning you're going to do power rule for this one. If you do power rule for this, that would be x minus 1 raised to negative 2 plus 1 over negative 2 plus 1. So your answer will be negative 1 over x minus 1. For x minus 1 raised to negative 1 over negative 1. So this is your answer. Plus C. If you intend to simplify by combining the ln's here, and you have subtraction, it would be ln of. So you have subtraction. So you have x squared plus 1 on top. This negative will be written here in the denominator, x minus 1 squared. The 2 came from in here in the coefficient. Then you have plus the arctan of x minus 1 over x minus 1 plus c. So this is the answer to the very long process of method of partial fractions consisting of a combination of factors. Any questions? So we have the linear factors, we have the repeated linear factors, and we have the quadratic factors. So any questions so far, class? Or any part here in the slide which you wish us to redo? So I will just reiterate that if you need to have this expanded so you can properly determine the coefficients of these variables, then do so. Okay? Then after you know the constants, you just substitute the constants in the partial fractions and then evaluate the partial fractions based on the techniques that you have already learned. Any questions? Okay, none. Oh, stop. Okay. Here. None. Sige. Wait.